Okay, hello, and welcome to Antenna Techniques for Advanced Magnetic Resonance Imaging with Professor Abbas Omar. My name is Rashonda Henderson, your host for this IEEE Microwave Theory and Techniques Society webcast. Before we start, I'll mention a few housekeeping items. First, this presentation will be archived. A recording should be posted approximately 24 hours after we finish the presentation. We will send all registrants an email when the archive webinar goes up so you can revisit it or share it with your colleagues. Second, we encourage questions. We'll answer them after the talk, but you can submit them at any time during the discussion. Enter your question in the Q&A box in the webcast window, and don't forget to click Submit. Third, some words about the interface. You can enlarge slides by clicking on the rectangle at the top right of the live slide window. You can also enter full screen mode if you desire. Refresh or reload the current web page if you encounter problems. With regards to audio, if you're listening over your computer speakers, you can adjust the media player volume. You may also need to adjust your system's master volume. The icons at the bottom of the webinar window include a resource list. Clicking that link will start the process to download copies of the slides to be presented today. Okay, let's introduce our speaker. Professor Abbas Omar received the Bachelor of Science, the Master of Science, and Doctor of Engineering degrees in Electrical Engineering in 1978, 1982, and 1986, respectively. He has been a professor of electrical engineering since 1990 and the director of the Chair of Microwave and Communication Engineering at the University of Magdeburg, Germany, since 1998. He joined the Petroleum Institute in Abu Dhabi as a distinguished professor in 2012 and 2013 as an organizer of the research activities for the oil and gas industry in this area. In 2014 and 2015, he chaired the Electrical and Computer Engineering Department at the University of Akron in Ohio, in the U.S. Dr. Omar has authored and co-authored more than 450 technical papers extending over a wide spectrum of research areas. His current research fields cover the areas of microwave, magnetic resonance, and acoustic imaging, microwave and millimeter wave material characterization, phased arrays and beamforming, massive MIMO, indoor positioning, subsurface tomography and ground-penetrating radar, and field theoretical modeling of microwave systems and components. Dr. Omar is also an IEEE Fellow. Now it's my pleasure to turn the virtual podium over to Professor Abbas Omar for Antenna Techniques for Advanced Magnetic Resonance Imaging. Abbas?
Yeah, thank you, Rashonda, for the nice presentation. Good morning, everyone. I believe that most of you are in the States, so it is morning. It's in Germany here, it's afternoon. So the title of my talk today is Antenna Techniques for Advanced Magnetic Resonance Imaging. I will find some parallels between what we use in antenna phase array and what can we borrow from this area to improve the what is called B1 illumination homogeneity in MRI. This is a short agenda of my talk today. I will start by having a short definition of what's imaging, move to the spin of elementary particles like electrons, protons, neutrons, and how to align these spins using strong magnetic field. And then we will discuss a special type of motion which is called precession. And then we will move to why it is called resonance, where is the resonance phenomena, and the accompanying loss mechanisms described by what is called in the community T1 and T2. Moving to the role of the RF field and polarization. Then distinguish between two types of magnetic fields involved in the processing. Show you the pulse sequence for constructing the image. And how can we, after collecting data, how can we make use of two-dimensional Fourier transform to reconstruct the image? I'll give you a quick overview on the constituents of MRI system, highlight the role of the RF coils, and then end the talk by talking about some borrowed antenna techniques for improving the RF coil performance, and then I will conclude the talk. Let us come now to the definition of imaging. Imaging is not more and not less than constructing two-dimensional or three-dimensional map of certain physical property. So if you have the physical property, for example, the material density in acoustics, so all what you are going to do is to find this material density as function of x, y, z. So for photography, which is known to all of us, the material property which we map is surface reflectivity. In acoustics or in what is called also sonar, ultrasonic imaging, it is the material density. There is also what is called microwave, millimeter wave, or terahertz imaging. In this case, we use the permittivity and or the conductivity. Especially in the MRI, we use a little bit strange quantity, which is the density of hydrogen nuclei in water. So actually, we are imaging water content, but through imaging of proton in the hydrogen atom within the water molecule. I'll move now to one of the fundamental property of elementary particles, which is called spin. Spin is a quantum mechanical quantity, so you cannot prove that it exists classically, but we can have a classical image or classical picture of it as if this elementary particle rotates around a certain axis. And any particle which rotates will acquire an angular momentum. And if the particle itself is charged, so this angular momentum is also accompanied by a magnetic dipole moment. Quantum mechanically, the ratio between the magnetic dipole moment and the angular momentum is a quantity which is called gyromagnetic ratio. The dimension of this, the units of this are frequency per unit flux density. And for protons in the isotope H1, it is about 42.6 megahertz per Tesla. Let us look to some of the known nuclei. For example, the isotope H1, which represents the high percentage of hydrogen. We have just one proton. We don't have any neutron. And the net spin is 1/2 multiplied by the Planck's constant. And the value of the gyromagnetic ratio is 42.6. If you consider the isotope H2, which has, beside the proton, you have an additional neutron, so you have 6.54. The ratio gamma itself, it is something like charge per mass, or the charge mass ratio. Therefore, if the mass increases, so the ratio itself goes down. So, and we have here for phosphor, for natrium, for nitrogen, and for other elements, just to give you some idea about that. You can also consider the electrons. Electrons, of course, they have much higher gamma because their mass is much less than the proton. Let us now consider these spinning charged particles like protons. Because of the thermal energy, they are directed in all directions, as you see in this view graph. To the left-hand side, they are directed in all directions. If you now apply a strong static magnetic field, which is shown here as B naught, they will align themselves either along parallel to the strong magnetic field or opposite to it. The opposite one has a higher energy contained in it because if you push it a little bit, it will lose kinetic energy and comes to the lower energy, which is called stable equilibrium. So both states are equilibrium. the one parallel is called stable, because if you push it, it returns back to its original state. And the higher energy, which is anti-parallel, is called unstable equilibrium. Of course, if you measure something from outside, let me come back. You will measure the net. So it is actually the parallel minus anti-parallel. And this is actually very, very small. If you look to the description of the whole thing in the classical mechanics, so the energy of the lower energy state is some background energy, which is irrelevant now for us, it's E naught, minus the product of mu, the magnetic dipole moment, times the applied static magnetic field. And this is actually the lower, which is directed along B naught. The higher is E naught plus mu. So the difference itself is twice mu times B naught. This quantity is really very, very small, so that measuring it from outside the body is really a challenge, an engineering challenge. Now let us come to how much is the difference between parallel minus anti-parallel, because actually what you measure outside the body is this difference. So Boltzmann gives us the statistic distribution. If you have two energy states, the number of particles in the higher energy state divided by the number of particles in the lower energy state obeys the Boltzmann distribution, which e to the minus the difference in the two energy states divided by Boltzmann constant times the absolute temperature. So and this number here, of course, or this ratio becomes less as we decrease the temperature. And this is actually better for us, because if it is less, we have more lower energy than higher energy, so that the difference itself becomes larger. Delta E itself is proportional to the applied magnetic field, as we saw in last view graph, so that if you would like to increase this difference, which means decreasing this ratio, you have to increase the applied magnetic field. So this is a summary of what I told you. So the net magnetic moment per unit volume is N times mu. N itself is the difference between lower minus higher. And as you see in this simple equation, it is proportional to the applied static magnetic field. We don't have anything else affecting this N except for the temperature. If you go the temperature lower, so you increase N, or to go higher with the applied magnetic field. But nevertheless, this M is still too small, so that we need very, very sensitive receiver in order to measure such a magnetic dipole moment. Just to give you a picture of the order of magnitude, if we ask for something like one Tesla, and we would like to put ourselves, so the body itself within this toroid, so we will see that the necessary current is something like 10,000 ampere. So just to have one Tesla. And one Tesla is actually very, very moderate for MRI. But the technical challenges here are the thermal loss, because 10,000 ampere, if you have any conductor, so the thermal loss is huge. Therefore, usually we use superconductors if we go over 3 Tesla. And this is actually the engineering challenge, or one of the engineering challenges in the whole process. We move now to a type of motion which is possessed by the spins, which is called precession. It's something like the top. If you remember your childhood time as you played with the top. So before the top falls down, beside the spinning, it makes another motion which is called precessing. And let us come now to, if I change the energy state of a spin from higher to lower or lower to higher. Although we are talking about the spin as tiny magnet, very, very small magnet, but it doesn't change like a magnet, but it changes by performing this precession. Whether you come from lower to higher or higher to lower, the motion of the proton in this case is precession. if you apply, in order to bring certain particles from higher to lower or lower to higher, first from lower to higher, you must inject energy. And this energy has a form of circularly polarized magnetic field with what is called the Larmor frequency. The Larmor frequency, we will see in next few graphs, is proportional to the gyromagnetic ratio, this gamma. So actually you must apply a circularly polarized magnetic field at the Larmor frequency in order to bring a certain particle from lower energy state to the higher energy state. Now, if you stop this exposure, the thermal equilibrium returns back, will be restored, and the particles return back to the to more lower energy than higher energy. But during this restoring of the thermal equilibrium, they radiate also magnetic, circularly polarized magnetic field at the Larmor frequency. This is actually, so this view graph here shows you how to describe the absorbing energy or emitting energy, once classical mechanically or quantum mechanically. This is the last one was for absorbing, which inverting the population. It is very, very similar to laser, because the thermal equilibrium, you have more lower energy than higher energy. And you should first invert the population, in which you bring more protons in the higher energy than the lower energy by injecting circularly polarized magnetic field. And then when you stop this exposure, thermal equilibrium returns back, and the spins themselves, they come back with more lower energy than higher energy. Of course, we are not talking about a particular proton. We are talking always on in sense of the average. If you follow just one particular proton, of course, it jumps between higher and lower very so stochastically. But we describe here the statistical average. This is a simple analogy to laser. For those of you who studied laser, in laser you have nearly the same principle. So in thermal equilibrium you have more lower energy particles than higher energy. You pump first energy in order to invert this population, and then you stop the pump. And in laser you have spontaneous emission and stimulated emission. And actually what we make use of in the laser is a stimulated emission, which is coherent in space and in time. We have here coherence in time, but we don't have in magnetic resonance coherence in space, because you can measure the magnetic field in all directions. Okay, why it is resonance? Because you need exactly the Larmor frequency in order to invert population. And when you stop your exposure, restoring the thermal equilibrium by emitting radiation, this emitted radiation is also exactly at the Larmor frequency. Of course, if we have lossless situation, the whole thing will last forever. But we will talk now next on some loss mechanisms which make this resonance finite Q. Of course, if you don't have losses, Q is infinity. Low loss means high Q, high loss is low Q. So therefore, we borrow the same expressions we usually use in electrical engineering with resonators. We have mainly two loss mechanisms in the magnetic resonance. One is the interaction between spins and lattice, because these spins are existing in tissues, and the tissues are composed of like any crystal, like any material. So they interact with the lattice, and with this interaction they lose energy, which means the thermal equilibrium returns back slowly by losing the energy to the lattice. This is called proton or spin lattice interaction. if you look to this view graph here, the horizontal axis is the time. Imagine now, and the vertical axis is the magnetic dipole moment in the Z direction. Imagine that you brought it to zero by flipping all spins to the horizontal or to the transverse plane. Okay, now you stop exposure and they will return back to the equilibrium, which is the maximum mz along the applied magnetic field by a time constant which is called in the community of magnetic resonance T1. The second loss mechanism is the spin-spin interaction, which means the spins themselves, when they precess, they influence each other and they start to dephase. When they flip, when they change the population, giving rise to more higher energy than lower energy, they are parallel to each other. But because of some slight differences in the precession frequency, they start to dephase. And if you look now to this curve here, they decay. Even if you bring them to the transverse plane, they will decay characterized by another time constant, which is called T2. And if you add, in addition to the spin-spin interaction, also irregularity in the tissues, this is another additional loss mechanism, which together with T2 gives rise to T2 star. Just to have some idea about the order of magnitude, the first column here are tissues in the brain, CSF, white cells, gray cells, and so on. T1 has the order of magnitude of seconds, as you see, from 0.8 seconds to 20 seconds. T2 is much worse because it has the order of magnitude of milliseconds. But nevertheless, actually, this is enough to perform the entire image reconstruction, as we will show yet shortly. Just to remind you what is temporally polarized, if you look to time-varying fields, you can distinguish between linear polarization, in which the electric or magnetic field has constant direction, only the magnitude change, or circular polarization, in which you have two components of equal magnitude, but they have phase shift of 90 degrees. So if you follow the electric field vector or the magnetic field vector, it is something which rotates, traces a circle. The general form is the elliptical, which is combination between linear and circular polarization. What we are interested in is the circular polarization. Okay, in the whole process, we deal with two types of magnetic fields. First, the static magnetic field, which aligns the spins, has an order of magnitude of Tesla. The LAMO frequency for our hydrogen protons is 42.6 megahertz for each Tesla. If you would like to use higher frequency, so you must linearly increase the static magnetic field. The other type of magnetic field is the RF magnetic field, which we use in order to flip the spins, just to invert the population. It must be circularly polarized, and if you consider this circular polarization, it is perpendicular in the plane transverse to the static magnetic field. It has two functions. When you apply it, it flips spins in the transmission scenario, and if you stop this exposure, the spins returns back spontaneously to the thermodynamic equilibrium, but during this restoring the thermodynamic equilibrium, they radiate exactly the same magnetic field at exactly the same frequency, which is a LAMO frequency, also circularly polarized. And actually, this is during this relaxation, we collect this field, or we measure this field and make use of it in order to reconstruct our image. Okay, let us see how can we flip. First, maybe some words about imaging and tomography. If imaging in general is two-dimensional or three-dimensional, the one-dimensional is trivial. But if you have a three-dimensional imaging and you make it slice for slice, this is what is called tomography. And this is actually what we are doing in the magnetic resonance imaging. In German, for example, it's called magnetic resonance tomography because it is done slice by slice. The first step is to invert the population in a certain slice. Therefore, you apply a magnetic field. I have here the vertical axis in this view graph. It is a Larmor frequency which is proportional to the magnetic field, as you see in the first equation here. So if you create a ramp in the magnetic field, say along the z-axis, as you see here, now each section of the body along the z-axis corresponds to a specific Larmor frequency. Now you excite at a certain frequency, which is called here F naught. This means only one slice will be excited, and within this slice, the population will be inverted. Okay, all other slices will not be inverted, so they are not exposed to their corresponding Larmor frequency, and therefore we actually have the image from this slice. Of course, the bandwidth is proportional to the thickness of the slice. The narrower the bandwidth, the thinner the slice, and the more accurate the image from this slice. Otherwise, actually, you average out. Therefore, it is important to have as less bandwidth as possible, therefore also the high Q performance, because high Q means the bandwidth itself around B naught is narrow. Okay, this was in the transmission scenario. Let us consider the receiving scenario. Because of these loss mechanisms, you need also high Q in order to catch the radiation before this T1 or T2 elapse. Okay, here we have, I will try to make some animation here. Left-hand side is the body. The vertical direction is the direction of the static magnetic field. We excite just one slide. I hope you see it now in the preview, in the audience view. So now we could invert the population at certain slice. Now at this slice, the spins are rotating. It's not rotation, but it is precession with the same Larmor frequency, with the same speed. Same speed, whether it is in the vertical direction, the y direction, or the x direction. So this is the first step in just exciting one slice of the body. The second step is to create along the x-axis phase difference. If you see here to the left-hand side, all over the slice, you have the spins are precessing in the same direction. Okay. Now imagine that you create a ramp in the x direction. This will mean that the right-hand side will be faster, for example, the left-hand side, and then you stop that. If you stop, you restore the uniform Larmor frequency all over the cross-section, but they will be dephased now. I will show you the animation. So as you see, right is faster than left, and it stops. And then afterwards, you stop this exposure, and you have now, you restore the Larmor frequency over the entire cross-section, but they are dephased now. As you see, they rotate along the x direction with the same Larmor frequency, but with different phases. So this way, we could assign a certain phase for each x value. So first, we picked up a slice. This is the Z ramp. The second step is to create a dephasing in the x direction. This is a phase difference, which is related to the x values. The last one is to create a ramp in the y direction, which results in different frequencies for different y directions, as you see in this animation here. We just apply the ramp in the y direction, resulting in higher Lamo frequency at the top and lower Lamo frequency at the bottom. Okay, now we created in this selected slice for each X a certain phase and for each Y a certain frequency. If we now collect the radiation coming back from the body, using a very, very simple Fourier transform, we can restore or we can reconstruct the image itself. This is here another animation. The first line, let it work. So the first line is the pulse so resulting in flipping the spins. The second one is the pulse you need for phase coding. The third one is the pulse you need. Pulse means now the ramp itself. You need for the frequency coding. Frequency is related to Y, phase is related to X, and now you acquire the signal or measure the signal coming back from the body. Okay, before describing the whole process a little bit more mathematically, so let us see to a very, very simple block diagram here. You have, this is the basic constituents of MRI system. You have the sample in the middle. Okay, and you have the RF coils responsible for slice excitation and receiving the back-radiated circularly polarized RF field. And then you have the gradient coils, which are responsible for causing ramp in Z direction, ramp in X direction, and ramp in Y direction. And you have the bigger magnet at the end is the static magnetic field B naught itself, which is order of magnitude of at least 1 Tesla. Okay, let us come now to some very, very simple equations. If you look to the first line here, we succeeded to have a Lamo frequency which is proportional to the Y coordinate. K dash is just constant. And we succeeded to have a phase which is proportional to the X coordinate. Now what we measure outside, if you look to the 1, 2, 3, 4, to the fifth line, you measure a collection of anything in the exponent of e to the minus j. You have a Y-dependent frequency and X-dependent phase. This is weighted by the concentration of the spins, which is, I called here a rho of X and Y. The whole thing is weighted with another weighting function, which is called W, X, and Y, describing the non-uniformity of excitation or reception. Because we use RF coils in order to flip the spins, we cannot claim that every individual point in the cross-section is excited the same way. You have it is something like antennas, and this is actually the beginning of making some parallels between antenna theory and MRI. Because this W of X and Y describes the transmitting property of the RF coils, whether the entire cross-section is homogeneously illuminated or not. And using reciprocity, you may also, or it is due to reciprocity, the transmission property and the receiving property are the same. So this W of X and Y describes actually the uniformity of illumination along a cross-section. If you look to this expression, you can just perform a two-dimensional inverse Fourier transform in order to have the product W of X and Y, this is the illumination uniformity, times the quantity which you are looking for, this is the concentration of the spins as function of X and Y. And as you see here, everything which you get is weighted by the uniformity of the RF magnetic field. Therefore, in order to have a uniform illumination or uniform image, we should have W of X and Y as uniform as possible. So something like 1 or something like constant. Okay, if you look now, so we performed a double Fourier transform We measure everything digital, so it is discrete. So actually what we measure is a function of kx and ky. So we must fill this square here in order to have usable information for the reconstruction. The whole thing is very time-consuming. Therefore, there are many methods for reducing the time for constructing an image, because this is just one slice, and you need here, if you have a resolution in the spectral resolution, say 256 points in the x direction, 256 in the y direction, so actually the time is huge. Therefore, we use something which is known in the signal processing by compressive sampling, which means we should reduce the number of collected data in order to work as fast as possible. So these are here some scenarios of how to collect the spectral data. Here it is radial. Here it is zigzag. Each scenario has its pro and contra. Here there's something else. Of course, it's not for fun, but each of these gives you some advantage regarding how to construct the image as fast as possible. We move now to the usually used RF coils. You have here what's called beard cage. Left-hand side is a real coil, which is so manufactured and used. The right-hand side is just a sketch of this. The whole thing is composed of two rings, and these rings are connected with racks. And between the racks, because if you only have the metal structure, you have inductive energy, so you will never have resonance. In order to have a resonance structure, you must provide some capacitors. And if you look to this slide, very thin places here, these are high-quality capacitors which are used to tune such a coil for the Lamo frequency. This is another type of RF coil. Usually it is multiple coils, something like phase array, which we use also in antennas. They are overlapped in a certain fashion, which minimize the mutual coupling. This is more suitable for head imaging. For such a coupled cavity structure, we try to minimize the coupling between the constituents, because if you have loosely coupled resonator, they will resonate at the same frequency nearly. If you have tightly coupled, you will get a number of resonance frequency, and this is actually not our aim. So we would like to have to use or to have the final resonance frequency of the whole coupled resonator structure very near to the resonance frequency of a single coil. So I move now to some field theoretical analysis of a beard cage coil. So I considered here 8 racks. So in order to simplify the analysis, so we assume that the racks themselves are strips, like you see here in the right-hand side. And for such a structure, it can support TEM wave or TEM field. If you describe each strip by a voltage, Vn, and a current, so you will have something like an impedance matrix description of such a structure. And I will return back to this view graph, because the coupling between 1 and 2 is exactly like the coupling between 2 and 3, or the coupling between 1 and 3 is like between 2 and 4, and so on. This impedance matrix has a very nice mathematical property. It is called circulant. So it has only just one, say the first row, and if you shift the first row by one place, you have the second row, by 2 places, the third row, and so on. And such circulant matrices have, whatever the matrix is, they have the same set of eigenvectors, which you see here, and the eigenvalues themselves are the discrete Fourier transform of the first line. This is very useful because if you look now to such a structure and consider the two components of the magnetic field, equations are a little bit complex here, but I will try to describe this. This is actually the dependence of the radial component of the magnetic field and the azimuthal component, depending on what is called the modal order. If you put here m equals 1, you will have something which is uniform. And therefore, m equals 1 is the required mode which we need in order to have high uniformity of the magnetic field. As I told you before, this uniformity of the magnetic field plays the same role the illumination of an image plays. So let us look here to the circularly polarized RF magnetic field of the first this m equals 1 mode. You see here, except for high concentration around the racks, you have uniformity. The only thing which you must take care of is how to excite this m equals 1 mode. Let me show you here. This is the left-hand side is B1 plus, which is actually the required field. B1 minus is the field which deteriorates the homogeneity. And for m equals 1, you have very, very nice distribution of the B1 plus, and you have nearly 0 B1 minus. This is for m equals 1. Therefore, you can, in the design of RF coils, you can concentrate on creating m equals 1 mode with high purity. And for this purpose, we use some concepts which we borrow from the antenna theory. You may excite all modes, and the number of modes is equal to the number of racks. If you have 16 rack coil, you have 16 modes. The only one which is important for us is the m equals 1. Therefore, you may use the concept of Butler matrix, which we borrow from antenna, in order to excite these modes in a certain balance. And if you put your body inside the coil, you deteriorate the m equals 1. Therefore, in order to restore the homogeneity, you can excite m equals 2, say 5%, m equals 3. With 3%, you can adjust. You have an adjustment between all these modes in order to restore the uniformity of the magnetic field. Therefore, I give you here a block diagram or the sketch of Butler matrix. A Butler matrix is a system which is known in the antenna theory, in which you can direct different signals to different directions. Okay, so imagine that you have an antenna array, and this antenna array can generate multiple beams, and the Butler matrix is a feeding network in which you can feed with, say, 5 signals, and each signal goes to a certain direction. The same concept can be used here for having a uniform magnetic field over the cross-section by the beams in the antennas correspond now to the modes of the coil, and the signals here, this is a mix between different strengths in order to have the uniformity or the magnetic field distribution along the cross-section as uniform as possible. Again, I would like to say something about this uniformity and its relation to the frequency itself. If you work with low Tesla or low Lama frequency system, like 1 Tesla, 2 Tesla, up to 3 Tesla, the whole thing, the birdcage coil and any excitation mechanism can deliver very, very good uniform magnetic field. The problem starts to arise when you go higher with the frequency. Of course, we don't have time now to relay the how can we increase the resolution of the image by increasing the Lama frequency or the applied static magnetic field. But the higher the static magnetic field, the higher the frequency. And as we know, the physical dimensions of a coil are limited by our body. We would like to put, say, a patient inside the coil. So you cannot decrease the dimensions of the coil below certain limit. As you know, in electromagnetics, everything is linear. So if you double the frequency, you can have the dimensions and you have the same performance. But we cannot have the dimensions because we should put a patient inside the coil. Therefore, we have to deal with structures which are, by raising the frequency, are comparable to the wavelength. And if the dimensions become comparable to the wavelength, we become propagation effect and the non-uniformity. Therefore, the non-uniformity of the illumination or non-uniformity of the RF magnetic field is a typical problem at high field magnetic resonance imaging. Starting 7 Tesla, 9 Tesla, there are something, I think the highest one which I heard about is 19 Tesla. So it's very, very, very strong magnetic field. But if you everything is linear because the lamp of frequency is proportional to the applied magnetic field. 7 Tesla corresponds to 300 megahertz. If we multiply by 3, so 21 Tesla, very near to 19 Tesla, corresponds to 300 times 3. So you are now working very, very near to 1 gigahertz lamp of frequency. And of course, if you limit, if you consider the constraints put by the coil itself in order to put your head inside or put your body inside, you have something like 30, 40 centimeter diameter, and in this case you have really multiple of wavelengths, and the deterioration of the homogeneity is huge. Therefore, such antenna techniques are more suitable for high field MR images. I come now to the end of my talk. This is a fast conclusion. I tried to keep the 45 minutes because we still have some minutes for questions. I gave you an overview on the fundamentals of MRI. Basic technical problems were described. We borrowed some concepts from antenna theory in order to make use of them for improving the uniformity of RF field. Of RF, the radio frequency field for exciting the slices and for acquiring the backradiated field. Thank you very much, and I'll be happy to answer your questions.
Thank you, Abbas. Very interesting presentation. Okay, it's now time for our question and answer session. So before we get started, I just want to remind everyone on the call that you are still able to submit your questions through the Q&A panel. One of the first questions that I have is, how do you test the coil arrays, Abbas?
To test them?
Right.
You mean, no. So you mean testing in which regards?
So the bird cage one that you showed, how do you test that for the frequency?
I see. So actually you have either to use simulator. Of course, this is actually in academic institutions we use simulators. So you can. There are many models for human body, which you can use in the simulator. You may also use infrared cameras if you would like to relate the heat, because you cannot measure directly. Either you say, okay, I will look to the image, and then of course you can give a subjective measure of the image or of the illumination of the image. You have hotspots, which means the magnetic field, the RF magnetic field was very high at these points, or very dark points where the magnetic field was very weak. So actually, from your subjective judgment of the image, you can have an idea about the homogeneity. This is one because actually how to put a sensor inside a body in order to measure the intensity of the magnetic field, it is not feasible. Therefore, either to produce the image or to use simulators by putting a model. I think there's the well-known Hugo model. You put, so it is actually a human being body with specified values of relative permittivity and relative permeability and conductivity at each point. And you can put it actually in your simulator in order to have the distribution of the magnetic field. This was your question, how to measure the uniformity. Okay.
Okay. Another question I had is, can you speak to the familiarity you have with the commercial systems that exist, the commercial MRI systems?
So the problem in medical applications, you may have a very, very good invention, but until it is approved, you may need a couple of years. Therefore, we actually split the work. So actually, you try to improve as an academic institution, and whether you have a contact with a company like Philips or Siemens, or you present your results in conferences and representatives of this company are there, so they will contact you. But the whole process, especially in medical application, is extremely slow. So even if you would like to change a very, very small thing, you have to go through many, many tests until it is approved.
I see. Okay. Let's see. And then one other question is, so typically the Lamar frequencies are a function of, as you said, the size of the coil.
I see. No, you mean the Lamar? No, Lamar frequency is proportional to the static magnetic field, the strong one.
I see. Okay.
Okay. But the Lamar frequency, the size, the physical size has constraints. Because if you would like to apply it to medical imaging, the size itself is not allowed to be below certain minimum.
Okay.
You would like to insert your hand or your head or your body inside. Therefore, in almost all microwave structures, you have a linear relation between the wavelength and the if you have an antenna working at say at 1 megahertz, say with certain performance, and you would like to have say the length of the antenna is say 10 centimeters, and now you would like to multiply the frequency by 10, just divide the dimension by 10, and you will have exactly the same performance. But you cannot divide these dimensions for MRI coils.
Okay, so there's still time for Q&A. Thank you for ending in a timely fashion. That way we have an opportunity, and there's still people on the call. So please feel free to upload your questions. Let's see. I know that I'm in the system. I don't quite see where it is. I know how to upload questions from my position.
I also don't see. I see only there is a button Q&A, but I only see your name.
Right. So, yeah, I'm actually in the. I'm logged in as an attendee as well, and I don't see. So our apologies. This is my first time being the producer, so let me go back. So there should be a Q&A box.
I have the box, but I see now in inbox you have 0, new folder 0, and trash is 0. I don't see, but I don't know whether I am allowed to see everyone or you as supervisor. I don't know.
Right. I'm looking for it on the attendee side, so that's where I don't see their option to enter questions. Oh, okay.
I will be happy to have any questions later if you can send to me per email, and I can respond with written answers if you wish.
Right. Okay. So I think that's what we'll do, and we'll apologize if there's something that we didn't set up properly to have the questions prompted because there should be a way for you all to submit them and for me to pass them on to Abbas. But as he mentioned, he is available, and we will send out an email, and I think at that point you'll be able to pass along those questions. So I think, Abbas, we'll go ahead and wrap it up. Is that okay?
Okay.
You? Okay. As we said earlier, this session will be archived on the Society website at mtt.org. All registrants will receive an email reminder with the website address when it is available to you. For attendees who would like to receive PDH credits, please follow the link. Let me go to the very last slide, and so that includes the link or the information about the credits. But you follow the link in the webcast view, and then you can use the code that's now provided for you on this last slide. So once again, I want to thank MTTS for sponsoring this webinar and Professor Omar for taking time out of his schedule to give us this excellent and informative presentation. Also, thank you to our audience for joining us today. We hope you have found today's event valuable and that you will return for future IEEE Microwave Theory and Technique Society webcasts. Thank you and have a great day.
Thank you very much. Okay, have a great day.